So since we were following our UVM process on our FPGA design, we had an SV wrapper to compensate for our DUT's lack of interface constructs in the system Verilog RTL, and oh hi! I didn't see you there. Did you think I was speaking some foreign language? Yeah, most FPGA designers don't know much about formal methodologies for verification. It's too bad, really, because today's complicated FPGA designs can really take advantage of standardized methodologies like UVM. But most of us are scared off by the alphabet soup of acronyms and seemingly bizarre concepts involved. It seems almost like a foreign language. Fear not, FPGA designing Chalk Talk fans, help is on the way. Hi, I'm Amelia Dalton, host of Chalk Talk. Today, with the help of my guest, Jerry Kaczynski from Aldec, we're going to unscramble the anagrams and get you on your way to understanding and harnessing the power of universal verification methodologies, so you can start applying them to your next design. And it's way easier than learning a foreign language. Heck, I'm starting to get it down already. Before we get started, I want to remind everyone that you can click on that Download Now button below your player. There you can download a free white paper that further expands on this topic. Welcome, Jerry. Thank you so much for joining me today.
Thank you very much.
So verification has become one of the most challenging parts of our product development process, to the point where we need some formal methodologies. What does this mean for hardware designers?
Very good question. Let's show some historical perspective first. In old good times, which in EDA terms, it means approximately 10 years ago, HDL designers were first creating Verilog or VHDL design code using stable standard versions, which means for Verilog it would be Verilog 95, and for VHDL it would be VHDL 93. Newer versions were showing up at that time, but they were not popular yet. And after creating code of the design, writing directed test bench in the same languages was most popular. What directed test bench is, it's basically speaking tests using fixed, predictable stimulus.
Okay.
System and verification engineers were happily using C++ or dedicated verification languages at that time. And here most popular ones include Vera and E. The only sign of new times was freshly developed System C standard. So it was announced, it gained some initial popularity, but it was not generally accepted at that time yet. So let's fast forward to now. And now we have newer, better versions of old languages. For instance, we've got System Verilog, second generation already, and VHDL 2008.
So we've got newer versions of language standards, and these languages have a lot of powerful features. It seems like it's difficult for many designers to understand how to apply that effectively.
That's a very good question, and let me answer with another question. Okay. Do you know how to recognize good programming language? The answer is that in good programming languages, more than half of active programmers uses less than half of language features.
Okay.
And definitely modern HDLs are powerful. They have logical syntax, complete and flexible type system, and they support high levels of abstraction. The only problem is that many HDL coders do not know how to use those advanced language features to reach their goals. And we do have a couple of examples here.
All right, Jerry, show us some examples.
Okay. Example number 1, randomness. Electronic designs have to deal with some level of randomness in real life. For instance, sensor data is random to some extent. The data traffic in communication systems can be treated as semi-random. User input can be random sometimes, or at least it should be treated as random to predict unexpected behaviors. Constrained random stimulus generation is, as the result, an important methodology in verification of large systems. For smaller systems, probably not so much, but if a lot of data traffic and similar issues happen in real-life design, constrained random stimulus will be very helpful. Unfortunately, majority of designers has imperfect level of knowledge of reliable random number generation.
Very true.
So what's our conclusion? We need better randomization support. So of course we welcome whatever language can provide, but some sort of wrapper around language that makes those features more useful is always appreciated.
Makes sense.
Okay, second example, coverage. When we deal with small designs or small blocks of larger designs, we can create test bench that will produce correct simulation results and exercise all behaviors of the design because the scale is relatively small. But in case of modern large designs with complex functionality, even most knowledgeable engineer may miss some design behaviors while creating test bench. So we need some additional methods of getting confirmation that test bench tested all important design behaviors, and even more important, that those design behaviors are the intended behaviors, not just something that happened as an accident while creating design description.
Absolutely.
So, long story short, we need special kind of verification methodology called coverage. We simply want to verify that those intended behaviors were properly exercised during verification. Third example, object-oriented programming, better known under acronym OOP, is a staple in software engineering. Unfortunately, it was never really embraced by hardware engineers.
Okay.
Please note that it's actually quite simple concept of packaging data and operations performed on it into just one entity. And here we've got idea of the package. That idea is called class, and actual implementation of that idea, which is called object. OOP helps to raise abstraction to the level required by modern system descriptions, and it also promotes reusability needed in system verification environments. So conclusion here is we need object-oriented programming, even if we are not aware of it.
Okay.
And last but not least, transaction level modeling, or TLM. Data exchange in modern systems can get pretty complicated. Both data formats and transfer protocols are contributing factors here. Transaction is one of the most popular methods of abstracting data exchange. When describing systems before they are implemented, we don't want to know what clocks, enables, data lines, etc. are used. We just want to state that data packet was sent from point A and received at point B. It simply means that we want to model system at transaction level, not at signal level.
I see, okay.
So, long story short, if we are dealing with large system, we cannot avoid TLM when developing those descriptions and when performing verification tasks.
So, Jerry, what does this all mean in terms of methodologies?
While programming languages may provide support of various techniques or paradigms, it usually targets experienced users. Average users tend to avoid the constructs they don't have to use. And the best example here is typical hardware designer. If you ask anybody working in support of simulators or similar tools, they will tell you that hardware designers try to avoid touching anything that is non-synthesizable.
That's true.
But even the most hardcore hardware designer has to appreciate verification. So if we can provide him generally accepted methodology, it can be very helpful because methodologies are easier to learn than the entire new language.
True.
They are also more reliable than code written by inexperienced users. And let's be honest, even the most experienced user at some time was the beginner.
True.
Methodologies promote interoperability. And it's very important because right now it's virtually impossible to write everything from scratch in-house. You have to rely on code written by somebody else, whether it's your colleague or manufacturer or some verification IP. So if we have interoperability at higher level, then our life is automatically easier. And last but not least, methodologies increase probability of code reuse. And again, we don't want to repeat the same task over and over and over. If we have already written something similar, we want to be able to quickly reuse it in our next design.
Absolutely. So a lot of engineers have heard of UVM, but don't really know what it is. Can we go into some detail about UVM, and what does UVM stand for anyway?
Okay, here it comes. UVM is a very nice acronym for Universal Verification Methodology. And since we already talked about methodologies, this acronym is pretty much self-explanatory once we expand it. From a more technical point of view, UVM is a library of system Verilog classes and other utilities that simplifies creation of advanced reusable verification environments.
Okay.
Please note that UVM requires at least basic understanding of object-oriented programming and transaction-level modeling. So you should know basic ideas, and the better your understanding, the more you can squeeze from UVM.
Oh, great. Okay.
Typical hardware designer can quickly learn enough UVM to do two things. First, use verification IP written by others, and second, work with verification engineers in his or her company on creation of new test benches. Of course, creating advanced UVM test benches requires slightly more knowledge and more practice.
That makes sense. So, for those of us who prefer a more visual presentation, what does this look like?
Okay, so let's have a quick look at this diagram. As you see, we have top-level module that currently contains a couple of elements. Let's start from the bottom, because we are trying to use bottom-up approach throughout this entire presentation. So at the very bottom, we've got design under test, also known as DUT, and some control logic that mainly consists of clock generators, reset generators, and similar stuff. They are connected together via system bus, and also via that system bus, they can talk to UVM class-based verification environment, which is, basically speaking, the core of UVM. What can we find in that pinky oval called UVM class-based verification environment? Of course, the first step is to create some data items that will be exchanged between all those blocks. Then we will need sequencers that will be responsible for handling data items. Then we need drivers that will be responsible for sending them to our design under test. We will probably need some monitors that will be observing responses generated by our design under test. We may need some scoreboards that will be analyzing those results as noted by monitors. And of course, there are many additional verification components that we can find, but those that are currently seen in our diagram should be enough to give you pretty good idea what to expect.
So we know what UVM means, but who is this useful for?
Okay, it's not a trivial question, not the easiest to answer, but let's try to provide as straightforward answer as we can. UVM works best in case of bus-based, high-traffic, system-level designs.
Okay.
So if you have all those criteria met by your design, then definitely UVM will be ideal for you. If you have at least some of them, then it's also worth trying. Please remember that UVM is the most efficient when verification procedures require randomization and/or functional coverage, because there are both UVM-specific and language-specific features that work very nicely in those cases.
Okay.
Of course, UVM can be adapted to handle other classes of designs, but may not be the best solution in those cases. Another thing worth to remember is that UVM uses mainly black box verification approach, so it does not try to reach into the internals of design under test. It just relies on the interface. So it should work with designs written in any language as long as the simulator that runs UVM supports all involved languages. Most typical example here would be UVM test bench working with VHDL design.
Ah, okay.
And of course, it should be self-explanatory that when you have system Verilog design, it can very easily work with a UVM test bench.
A lot of hardware designers have no idea how to connect their designs to a framework like this. How do we get started?
Okay, long story short, class-based part of UVM communicates with RTL design under test, our DUT, via System Verilog interface construct. New System Verilog descriptions of design under test can already utilize interfaces, but what to do if they don't? If your design under test does not use interfaces because it is written in Verilog or VHDL or something similar, you can consider creating System Verilog wrapper with interface around it.
Okay.
The less UVM test bench knows about DUT implementation details, the better. So that's why that wrapper approach is actually very good idea.
So, Jerry, what's so special about the System Verilog interface construct?
Interface can be treated as universal signal container.
Okay.
So current diagram shows us such a container. Let's concentrate on the central part labeled my_IFC. That's the real container. As you see, it contains a couple of lines: clock, reset, enable, data in bus, data out bus, and ready signal. So that's pure signal container. We can even say that system interface is module level container for signal and port direction data. How about the direction data? We've got attachments on three sides of that interface container. They are called mod ports. So while interface itself just says, okay, I've got clock, reset, enable signal, and some more, mod ports are specifying what's the direction when you try to connect that interface with other modules in your design. We also have matching System Verilog code that shows us that although mod ports specify connections of that interface to other modules, they are actually defined inside that interface. In our case, we've got three mod ports: slave, master, and monitor. And as you see, they are repeating the names of signals in the body of interface. They are just adding input-output qualifiers. Please note that many beginning users confuse those directions. That's why our diagram shows little yellow letters module and bus. So you can see that master has clock line labeled as input.
Okay, I see that.
It means that it is input on the side of module. If you try to look at the System Verilog interface description as it is in the code, it's not really how a signal is seen from within interface, it is how it is seen from the block that connects to that interface.
Oh, okay. Okay, so it looks like interfaces is something more for the hardware domain. How do we use this in an object-oriented environment?
Very good question. It's actually one of the most critical parts for understanding of UVM. As we have mentioned in previous slide, SV interface is a module level construct and it cannot be used inside class, which is programmatic construct. But you can have virtual interface as a class attribute. Class attribute is just something that sits inside the class. And if you have virtual, not plain interface placed inside any class, it is treated as a pointer to real non-virtual interface. Pointers are quite common element of classes, so it should not be alien to anybody who does object-oriented programming.
Good.
We've got little problem here. Pointer has to point to something. By itself, it's pretty much useless. So virtual interface must be tied to real interface if object plans to do anything with it. And of course, we want our UVM test bench to do something.
Sure.
How it can be achieved? You can assign real interface to virtual interface in the class constructor. That's a very basic element of object-oriented programming. So it can be done, but it's not really recommended in UVM because it would cause a little bit of problem. So what can we do instead? We can use UVM Factory and configuration database. Those are two important features that we'll explain a little bit later, to tie virtual interfaces to their real counterparts. So please remember, if it's your first contact with UVM, Virtual interfaces are the only area of UVM where transaction level modeling world meets register transfer level world. They are also one of the least popular system Verilog constructs, so even quite experienced system Verilog users, especially if they are creating hardware, they probably haven't heard about virtual interfaces, even if they heard about plain interfaces. A lack of understanding in this area is one of the main reasons of hostility towards UVM.
I see. Okay. So I just heard a lot of hardware designers' minds getting blown there. Jerry, show us some practical implementation.
Okay. Let's try to use flow or workflow approach here. We have covered background information, and let's use bottom-up approach, which is best suited for hardware designers. We will see a couple of next slides. The first will introduce non-class based elements of UVM test environment, and then gradually, following slides, we'll introduce class-based elements from simplest to more complicated.
All right, Jerry, show me a picture. I need a picture.
Okay, let's start with the framework. It's sort of blown up version of our very first diagram, because we are going to provide more detail here.
Okay.
As you see, we've got our top level module. That's our highest level wrapper, something that simulator users know as top level required for simulation. And inside, of course, we have to instantiate our design under test. We already know that interfaces have mod ports, so our DUT will be talking via mod port to system Verilog interface instance. So again, sometimes system Verilog terminology seems a little bit unfortunate. Here, that instance of interface is not really interface. It just works as a bus.
Okay.
Of course, design under test requires some additional control logic. So things like clock generator, system reset generator will also be talking to that bus, which is system Verilog interface instance. And we will have our UVM class-based verification environment, as we have seen in our original diagram. When we want to add anything to UVM class-based verification environment, the first thing should be one of the data items, because before we create something that processes data, we should describe our data properly. And the smallest chunk of data that can be transferred within our environment is called sequence item. That's UVM terminology, but we can call it packet for our application here.
Okay.
That's just one chunk of data, so probably it would not be the most impressive and would not let us do a lot of interesting things. That's why we are multiplying those packets and combining them into sequences.
Okay.
And definitely sequences will be used very frequently in any kind of UVM environment. Okay, to handle our data items, we need some verification components, or VCs, as you can see them described on some smallish diagrams. And as we see in current diagram, three kinds of verification components are very frequently, almost always visible. They are monitor, sequencer, and driver.
Okay, Jerry, wait a second. What are those red and green and blue things? Are we playing Bejeweled here?
Almost. Actually, we are playing transaction level connections here.
Okay.
All verification components, when they have to talk to each other, use transaction level communication ports. And in our case, driver has something called port, sequencer has something called export. That's why we are using different shapes and colors here. They have nothing to do with exporting things. Basically speaking, export is the port that is responsible for implementing transaction, while that green port thing is responsible for requesting that particular transaction. The blue diamond in this particular case is very special kind of port called analysis port. We will see how it can be used a little bit later. So, of course, now we've got our data items, we've got 3 verification components. It would be good idea to start connecting them. And as you see, the first connection would be our transaction level connection between sequencer and driver. And we also see 2 new elements showing up at the bottom of monitor and driver. Those are our virtual interfaces.
Ah, so those are the same virtual interfaces that were confusing us earlier?
Exactly. But please remember, as long as you remember to create that arrow, which is establishing connection between pointer and actual interface in our environment, we should be fine, and we can do it once right before simulation. So it may sound confusing at the beginning. Once you do it at least once, it will be pretty routine procedure. Please note that what we currently see in the diagram is not the most sophisticated UVM, but fully functional one. So if you are starting your adventure with UVM, it's probably the first simplest kind of test bench you can create, which of course raises question how you can simulate something like that.
Right.
The good part here is that if you have at least one environment available in your UVM top-level module, then you can just execute run test task. That's why that orange block popped up at the bottom of our diagram. And that's it. If you just say run test, you don't have to mention what's the name of that environment. If there is just one, it will be automatically picked and executed. There is one more step that may be worth doing. Right now, as we see it, it's maybe not well justified, but for future use, it's frequently recommended to wrap sequencer, driver, and monitor into new entity called agent.
Okay.
It is especially useful if you can parameterize your agent. So if there are parameters governing sequences that are generated and data that is observed by monitor, then if you create agent, everything starts fitting very well together when you develop your test bench a little bit further.
Okay, I see.
Please note that so far we've got very basic structure. So we've got some data driven to our DUT and some data read back via monitor. If we want to actually do something with the data, we need additional components. And the best example here is Scoreboard. As you see, it is nicely tied to the analysis port of our monitor. And of course, what it does depends on the nature of our design and the tasks that we plan to accomplish while doing our verification.
So, Jerry, does this mean that Scoreboard needs to be placed in the environment, or can it be placed anywhere else?
I guess that connection that crosses border of agent is a little bit confusing here, but it's actually a feature, not a bug.
Oh, okay.
Scoreboard uses transaction level connection between analysis port and its own export, and it means that that connection can be created anywhere and at any time. So you can have Scoreboard in any convenient location. Usually it is not placed in the agent, so environment seems to be pretty natural element. As we start seeing more complicated UVM test benches, we will see that those scoreboards can migrate to those other areas.
I see, okay.
So we have mentioned complication of our environment. As you see, we are doing some resizing just because we will see a little bit more elements here. So for more complex design under test, hierarchy of our UVM test bench can get more complex.
Are you kidding me, Jerry? This is going to get more complex?
Don't worry, just a little bit more complex, but please know that when we are at the higher levels of abstraction, things are usually easier. There are less details to handle. So as you see, the first possible complication is adding more agents. Agents usually should deal with relatively narrow tasks. So if you have multifunction design under test, it will be quite natural to see multiple agents.
Okay.
Here we see just example of one environment dealing with one interface represented by that bus block. But please know that more complicated designs may actually have multiple interfaces. It would be perfect example, perfect justification for adding more environments. So usually, even if you have one interface, multiple environments will be justified. If you have multiple interfaces, they will be practically required. So we can have multiple agents in our environment. We can have multiple environments, but we can build that hierarchy even further. So our multiple environments can be wrapped up into a test. While environments will be responsible for those narrow tasks, test will be responsible for tying everything together and providing appropriate synchronization for those environments. And probably you have not expected it, but we can actually have multiple tests. Good news here is that only one test is active at any given time. So having multiple tests simply means that you are well prepared, and if results of test 1 are not satisfactory, you can simply deactivate it and switch to some other test.
All right, I think my brain is almost full. Is this everything, or is there more?
There are actually a couple of features that are not easy to represent on diagrams, but they are still very important.
Okay.
Probably the most spectacular feature, once you learn how to use it, is UVM Factory.
Oh, Factory, of course.
It is one of the essential features, class-based verification components. To understand Factory, we must remember that one of the essential features of class-based verification components is that they are dynamically created. And please remember, it is very different from the RTL hardware models, which are always statically created. So before you start simulating them, they are already fully instantiated and configured. UVM Factory lets you register object types while you write test bench, because at that time you definitely know what objects you need or what objects you may need, but it postpones the process of creation till runtime. So you register objects while you write, but create objects as they are needed at any time during simulation.
Okay.
You can also register data fields of objects as so-called knobs. Why to do something like that? Because later you can override, which means modify them as needed during test run. Again, you can do it at any convenient moment. So you can modify those knobs before you instantiate new component, after you instantiate it, and let's say when you change test, such modifications are also possible. So long story short, UVM Factory, which lets you create new objects, together with configuration database, which stores all those knob data, provide excellent flexibility. And again, no matter of talking will convince you here. You would have to actually create your first test bench to see how nice feature it is.
That's true. So, Jerry, for those of us who need a real code example, can you show us something along those lines?
Okay, no problem. Let's have a look at class called Packet. Please note that although it's relatively simple, it's fully functional, so it can be compiled and it can work in test environment. Actually, it was taken from working design. So, first thing, please note the sequence of words. Class Packet extends UVM sequence item. That's the proof that we are dealing with so-called inheritance. So UVM sequence item is something sitting in UVM library. You just fine-tune it by extending or inheriting from that class, creating your own packet class. Inside, we've got two attributes or data members. Different people prefer different terminology here. Please note rand keyword at the beginning of each of those two declarations. It means that those two data members are ready for randomization. Then we've got a couple of macros. Those who use Verilog or System Verilog should be familiar with the tick at the beginning.
Mm-hmm.
The first macro that you see starts the entire group of macros, and it is responsible for registration of this particular object type with UVM Factory. Then we've got two dedicated field macros, and they are repeating names of our data attributes. So we've got both data and address handled here. Those are our knob registrations. Please know that for somebody who sees it for the first time, it may seem a little bit complicated, but believe me, if you are forced to do very low-level direct System Verilog code to achieve the same results, you would get real headache. So you should really appreciate those macros. Once you know how to use them, it will be routine procedure and will provide you with the wealth of features.
Great.
Then we've got something that deals with a very specific area of randomization, namely constraints. If we look at our data fields, they are defined as plain integers, and as we know, integers are pretty big numbers. Without constraints, we would get unrealistic data during randomization. With constraints, we can be more specific. So first we say that our data should be between 0 and 100 hexadecimal, and address should be in slightly wider range. So long story short, if you translate it into bit level data, you would say that we request that data field should be 8-bit and address field should be 10-bit.
Okay.
The remaining part is standard class constructor, nothing really revolutionary here. So we have just defined packet. If you look back at our diagram that we have seen a few moments ago, we said that our packets should be combined into sequence. So let's see how it can happen.
Yeah.
Here's another example. Class mySequence, which extends UVM sequence. UVM sequence always requires parameter that specifies what kind of data our sequence is processing. So that's of course our packet we have seen in the previous slide. We've got nice field which specifies what's the number of packets that should be generated by our sequence. Of course, this particular data field is immediately registered so that later when we use our sequence, we can adjust it easily. Then of course, we've got constructor, nothing special here. The critical part of sequence description is task called body. So you are not supposed to call it any other way. Call it body, then system knows that that's the area where functionality of sequence sits. Of course, we declare a local copy of packet, just to simplify handling of the entire sequence. Then UVM info, it's just a very good way of injecting debug information. So when we run our test, we will see what's happening at any given moment. Then we have for loop. As you see, it's executed precisely n packets times. And it uses yet another nice UVM facility, UVM do macro. So instead of manually creating new packet, randomizing that packet, waiting for grant, sending request, waiting for done, all those things would have to be done manually. If you use that UVM do macro, you just specify the packet that should be handled, and that packet will be created, randomized, and properly synchronized during execution phase with other elements of our test batch. And of course, at the end, we've got yet another info stating that we are done with processing of our sequence.
Okay, so after we follow the steps you introduced earlier, where do we go from here?
Okay, so now we've got packet defined, we've got sequence defined. Now we have to attach our sequence to UVM sequencer, because UVM sequencer will know how to deal with sequence once execution starts. But the sequence we have defined is definitely operating at transaction level, while our design under test requires changes of individual lines, such as clock line, enable line, data lines. So we need UVM driver, because that's the main task of driver. It translates transaction traffic that comes from the sequencer into signal level traffic required by our design under test.
Okay.
Of course, we typically expect that our design under test responds, so we want to verify if it's correct or incorrect response. That's why we need UVM monitor. It plays sort of opposite role to the driver. So it observes signals and data that comes from design under test and recreates transactions based on that observed data. And of course, you can create all those elements, all those verification components easily, but we do not have enough time to deal with it, although we could probably talk about it for next couple of hours. To see how to create those and other verification components, check out Aldec training called Fast Track to UVM. Just visit our website and you can learn more.
Okay, I think I understand. Can you show us a summary of the whole workflow for creating a UVM test bench?
Okay, here it comes. Of course, we are skipping the important step of creating design under test because that would be totally different training. We have to verify before we proceed any further if we have proper interfaces. So if DUT already has interface, we are fine. Otherwise, we have to create wrapper. Once we have interfaces established, we can start creating data items. And again, bottom-up methodology here works best. So first we define packet type, then we tie packets into sequences, and we can build data hierarchy even further if we need.
Okay.
Once we have data items, we need sequencer and driver. Sequencer will be just processing sequence item by item, sending those items to driver, and driver will be translating transaction data into signal data.
Okay.
Then, of course, DUT will be processing data, sending some responses, and monitor. We have to create monitor to observe responses coming from our design under test. If we plan to reuse whatever we have created so far, we can create agent. That's just component that wraps together sequencer, driver, monitor, and let us make it more flexible and reusable. Of course, when data created by sequencer and driver reaches design under test and then we observe responses via monitor, we usually want to process the data a little bit further. So we should consider creation of result checkers, such as Scoreboard that we have seen in our diagram earlier.
Okay.
Once we have our agents and checkers, we should start organizing our environment. We've got dedicated environment construct, which ties together our agents, scoreboards. And we can also create higher level tests that are ready to be run from top level module which completes our entire process of creating UVM verification environment.
Phew, that has been a lot of information. I think I'm gonna need to sign up for one of those classes.
You are welcome, of course. Let's try to summarize what we have seen here. We have introduced UVM as methodology. And please remember, verification methodologies can be very useful, especially when quick results are needed. Methodologies promote interoperability and reuse. Experienced users, however, may notice that in some very specific applications, solutions written from scratch is better than the one offered by methodology. It does not happen very frequently, but it can happen. That's sort of penalty for using methodologies. Although UVM is called universal verification methodology, you can find cases where it's not the best solution.
Ah, okay.
So we can say that in many cases methodologies are ultimate blessing, but in some specific cases then they can be necessary evil. So you are forced by company policies or some customer requirements to use them. They usually work. They may not be the optimal, but they definitely will get you to your final result. But again, those are exceptional cases. Usually they work pretty smoothly.
Okay, Jerry, Tell us where we can go for more information.
Okay, the best idea is to visit our website www.aldec.com. You can send email to sales. If you want to reach our US office, there are also some email addresses that will let you reach our offices located worldwide. You can call us if you want. If you want even more detailed contact data, of course, website will provide it. If you want to check schedule of our trainings, webinars, and other events, it's also available on the website. And of course, you can learn about our other products too.
Well, great. I think that's all I have time for today. Thank you so much for joining me today, Jerry. It was a pleasure speaking with you.
You are definitely welcome. Thank you.
And before we go, don't forget to click that Download Now button below the player to download a free white paper that further expands on this topic. For Chalk Talk, I'm Amelia Dalton. For more Chalk Talks, check out the On-Demand section of eejournal.com.